Angle misclosure. The topics covered include the polygon traverse misclosure, the link traverse misclosure, and allowable closure for a traverse. Polygon traverse misclosure. The misclosure is the sum of the measured interior angles in the polygon as compared to the geometrically correct sum of interior angles. In equation form, this means that the actual closure is equal to the sum of the interior angles minus the geometrically correct sum of angles in the traverse. The geometrically correct sum of angles is always n minus 2, where n is the number of interior angles in the traverse. As you can see in this sketch, we have a six-sided traverse with 6 interior angles at A, B, C, D, E, and F. And if we summed up those 6 angles, they should equal 6 minus 2 times 180, or 4 times 180, about 720 degrees. Of course, in the field, these angles will never add up to exactly 720 degrees, but they will add up to something very, very close to that. Link traverse misclosure. Link traverse misclosure is the difference between the measured closing azimuth mark and the known closing azimuth mark. In equation form, the actual misclosure is azimuth mark measured minus azimuth mark known. So if we look at a link traverse, we can see that we start a link traverse with a known azimuth. Setting at point A, we can observe the azimuth mark 1 and find the azimuth of A to azimuth arc 1. Turn all of our angles to the right at A, at B, C, D, and E. The angle to the right at E will find us lined up with the azimuth mark at 2, and this is the measured azimuth mark, and then we will compare that to a known azimuth mark which we have determined in the field or found in the field through some other survey. The allowable traverse misclosure. The allowable traverse misclosure is based upon a level of accuracy specified for a traverse survey. The National Geodetic Survey Federal Geodetic Control Subcommittee on Traverse Survey Standards provides the equation that C allowable is equal to K times the square root of N, where K is a constant in seconds based upon the order of accuracy in the traverse survey. We can see that first order of accuracy work, K is equal to 1.7 seconds, second order class 1 work, 3 seconds, second order class 2 work, K is equal to 4.5 seconds, and so on as we go down the list clear to third order class 2 work, where K is equal to 12 seconds. Let's look at a couple of examples. Let's look at a 4-sided polygon traverse ABCDA with measured angles A equal 89 degrees 15 minutes 37 seconds, B 91 degrees 7 minutes and 22 seconds, C is equal to 120 44 52 seconds, and D is equal to 58 degrees 52 minutes and 01 seconds. In this particular problem, what we'd like to find is we'd like to find the traverse angular misclosure and order of accuracy of the survey according to NGS FGCS specifications. So this is a traverse survey for a polygon, and the solution is, as we presented earlier, we need to find the sum of the interior angles and compare that to the geometrically correct sum. So let's list the angles according to station. Station A was 89 degrees 15 minutes and 37 seconds. B was 91 degrees 07 minutes and 22 seconds. C was 120 degrees 44 minutes 52 seconds. And D was 58 degrees 52 minutes and 01 seconds. All we need to do is just add up these 4 angles and see what we come up with. So if we add these up, we see that in the seconds column we get 112 seconds. In the minutes column we get 118 minutes. And in the degrees column we get 358 degrees. We need to put this in a more standard form, so we take this and look at the seconds and realize this is actually 52 seconds plus an extra minute. So it's 119.52 plus a 358 degrees. But again, this is not in a standard form. We need to get this into the range of 0 to 60 minutes. And so this is really 59 minutes plus an extra degree, or 359 degrees, 59 minutes, and 52 seconds. So the sum of the angles reduces to 359 degrees, 59 minutes, and 52 seconds. We'll take that sum and we will subtract it from the geometrically correct sum. 4 interior angles minus 2 gives us 2 times 180, or that's 360 degrees. So the actual closure is 359, 59, 52 minus 360 degrees. we can see that the actual closure is a negative 8 seconds. So that answers the first part of our problem. The second part, we look at survey order of accuracy. And again, the equation given to us by the FGCS subcommittee on traverse standards says that the allowable closure is equal to k times the square root of n, where k is one of these values based upon the order of accuracy of the survey. Well, in our case, what we'd like to do, instead of trying to compute an allowable closure for each one of these cases and seeing if it matches or equals the actual closure that we encounter, let's just do something different, and let's compute an actual k value for our traverse and compare that then, our actual k value, to something in this table. Our actual k value is equal to the absolute value of the actual closure divided by the square root of the number of interior angles. We can see that this result gives us 8 seconds divided by 2, or 4 seconds. We'll take our k actual value and start comparing from the bottom going towards the top. We can see that the 4 seconds definitely satisfies third order class 2 work. We only needed 12 seconds, and our survey provided 4. It also satisfies third order class 1 work because we have provided 4 and we only need 10. Similarly, we've also satisfied second order class 2 work. We need 4.5 seconds k, where we have actually a k value that's better than that. It's 4 seconds. So we certainly are providing second order class 2 work. When we get to second order class 1 work, we see, however, that we fail. We would need 3 seconds k value, where our actual k value is 4. We do not meet second order class 2 work. Therefore, we can summarize that the survey satisfies second order class 2 survey work, and that provides the second answer to our problem. Let's look at a second example, a link traverse. A link traverse with azimuth from A to azimuth mark 1 is north 27, 37, 57. The azimuth from the last station to azimuth mark 2 is north 118, 27, 25. Angles measured to the right at each station are as follows. A is 119 degrees, 14 minutes and 07 seconds. B is 95 degrees, 00 minutes and 08 seconds. C is 244 degrees, 51 minutes and 36 seconds. And the last angle D is equal to 171, 43, 45 seconds. What do we want to find? Just like the previous example, we want to find the traverse angular mixed closure and the order of accuracy of the survey according to NGS FGCS specifications. Our solution is to compute the azimuth of the line D azimuth mark 2 and compare it to the known value. We've already specified the known value from the last station to azimuth mark 2 is 118, 27, 25. So we're going to compute this D azimuth mark direction, and this direction should be very close to this 118, 27, 25. And then once we find that, we will take the measured value and we will subtract it from the known value and get our actual closure. Let's summarize the given data then. We know that the azimuth from the first station to the azimuth mark is 27 degrees, 37 minutes and 57 seconds. We know that the first angle measured at A is 119, 1407. The angle at B is 95 degrees, 00 minutes and 08 seconds. The angle at C is 244 degrees, 51 minutes and 36 seconds. And the angle at D is 171, 43, 45 seconds. The azimuth mark from the last station in the traverse to the azimuth mark 2, the direction is known to be 118 degrees, 27 minutes and 25 seconds. What we would like to do is, taking this data right here and with this beginning information, compute what this azimuth should be. So let's set up a table and let's look at what the azimuth should be. We'll start with the given azimuth sitting at A, looking at azimuth mark 1. We know the direction is 27, 37, 57. And so we're sitting at A, looking at the azimuth mark 1 and turning to B. We can just simply add the angle at A. There's no need to compute a back azimuth. We already have the azimuth from A emanating from A towards the previous mark, which is mark 1. So we'll just add the angle to A, and we'll get the two to add up to 57 plus 7 is 64. Well, 64 is outside the range of allowable seconds, so we'll make this 4 seconds, take the extra 60 seconds and add it to the minutes column. We'll get 11, 12, carry the 1, we'll get 52 minutes here, and again over here we'll get 146 degrees, 52 minutes and 04 seconds. That's the azimuth from A looking at B. We want to now change the direction of that azimuth and get the azimuth from B to A. And so we either add or subtract 180 degrees, whichever value gets us between 0 and 360. Well, we can see that if we add 180, we're going to be less than 360. If we would subtract 180 here, we would have a negative number, and we can't have that. So we must add the 180 degrees, and we'll get an azimuth of 326, 5204. 326 degrees, 52 minutes, and 04 seconds. Now we have an azimuth at B emanating directed towards A, and we have the angle at B. We can simply just add the angle B and get the azimuth from B to C. So this 4 plus the 8 is 12 seconds, 52 minutes, and 421 degrees. This azimuth is outside the allowable range of 0 to 360 degrees, so we must subtract 360 degrees from this to get the actual azimuth from B towards C. And we find this to be 61 degrees, 52 minutes, and 12 seconds. Now we have the azimuth from B to C. We want to continue with the process. The process says that we must get the back azimuth of this line. So to get the back azimuth, we either add or subtract 180 degrees, such that the forward azimuth is between 0 and 360. We can see that adding 180 gets us around 240. And so we definitely want to add the 180 degrees to the previous azimuth. To get the azimuth from C to B, it is now simply 241 degrees, 52 minutes, and 12 seconds. We'll just continue these calculations. We'll just start with this last line here, and we'll place it on top of the screen and just keep on going. So we have the azimuth from C to B. The next thing we want to do is simply add the angle at C, and the angle at C that was measured, it's over here, 244, 51, 36. So add that angle, and we're going to see that we're going to get an azimuth of C to D of 486, 43, 48. And again, just keep in mind here, we're adding the 52 and the 51 together, getting 103. That 103 really is 43 minutes plus 60 minutes, and 60 minutes is 1 degree. So we'll take the 1 over here and add this, make this a 2, a 4, we'll make this a 6, 486. Again, this is outside the allowable range for the definition of an azimuth, so we must subtract 360 degrees. That subtraction gives us a result of the azimuth from C to D of 126, 43, 48 seconds. Now we want to go to the azimuth mark, so we need to change the direction from C to D and get the azimuth from D to C. So we either add or subtract 180 degrees. Again, in this case, we must add 180 degrees. If we were to subtract 180 degrees, we would get a negative number here, and that's outside the allowable range for definition of an azimuth. So add the 180, simple addition here. We have 306 degrees, 43 minutes, and 48 seconds for the azimuth from D to C. And now we need the angle at D. Just add that, and we'll get the azimuth mark direction from D to azimuth mark 2. At least we should. Let's look at this. Well, we get 10, we get 100 over here. That's going to give us 100 is actually 40 seconds plus 60 seconds, which is 1 extra minute. The 243s gives us 86 plus 1 is 87. Well, that's really 27 plus 60 minutes. Take the 60 minutes, come over here and make it a degree, and this becomes 307 plus 171, or 478 degrees, 27 minutes and 40 seconds. We must again subtract 360 degrees, and we get the azimuth from D to azimuth mark 2 to be 118, 27, 40. We can see this is the actual computed or measured value. What we know from a previous survey or from some given information prior to our survey, someone has established this azimuth mark to be 118, 27, 25. Well, we have 118, 27, 40, so we can see there's a disparity here. We'll find out what that is. What we need to do is just subtract the two. So the actual disclosure is the azimuth mark measured minus the azimuth mark known. The measured was 118 degrees, 27 minutes, and 40 seconds. The known was 118 degrees, 27 minutes, and 25 seconds. So our actual closure is 15 seconds. And that answers the first part of our problem. The second part is, what's the order of accuracy of our survey according to FGCS standards? Well, again, we use the same exact equation as we did in the polygon traverse. C allowable is equal to K times the square root of N, where K is one of these values in this table here. Again, instead of trying to compute the allowable closure for each one of these survey types or classes, let's just solve for our own K value. And so our own K value for our survey is the actual C value, which was 15 seconds, divided by the square root of n, where n is the number of angles measured. So it's 15 seconds divided by, we had 4 angles measured in this case also, just like the polygon traverse problem. So it's 15 divided by 2, or 7.5 seconds. Taking this actual K value and compare it to the allowable K values, we can see that we definitely satisfy third order class 2. We definitely satisfy third order class 1. We do not satisfy second order class 2. So we are going to claim that our survey satisfies third order class 1 survey work. In summary, we've covered 3 topics. The first topic covered is the polygon traverse misclosure. The second topic we covered was the link traverse misclosure. And the third topic we covered was allowable closure for either the polygon or the link traverse. The outcomes that we hope you take away from this video lesson are: 1, you have the ability to compute polygon traverse misclosure. 2, you have the ability to compute link traverse misclosure. And 3, you understand how to classify a survey according to FGCS standards. This is the end of this video lesson.